Hi, in this video I am going to explain how to do stiffness method of structural analysis using MATLAB. Let us consider an example from the NPTEL materials. The given problem is a 2D truss with 4 nodes and 6 members with a span of 5 meters and a height of 5 meters. This is a redundant structure with one internal redundancy and 2 external redundancy. 2 external forces are given. So before getting into the problem, let us recap the general steps involved in matrix stiffness method. So the first step is we have to number the nodes. The second step is we have to number the members. Then we have to identify the location of each node in the Cartesian coordinate system. Next we have to identify the global coordinates. So for this particular problem, the nodes are numbered as 1, 2, 3 and 4. And the members are also numbered as 1, 2, 3, 4, 5 and 6. You can note there is no intersection between the members of 5 and 6. The next step is to identify the global coordinates. Each and every node has 2 global coordinates, one in the horizontal direction, the other one is in the vertical direction. So for 8 nodes we have 8 global coordinates. Our next step is to write element stiffness matrix for each elements. So in our case is a truss problem. So the stiffness matrix is given by AE by L, and you can see the cosines here. So it is cos square, cos theta, sin theta, cos theta, sin theta and sin square. These are 4 elements taken in the negative sense here, and here is also negative, and here it is taken in the positive sense. So after writing the element stiffness matrices, we have to assemble them into global stiffness matrix. So in our case, for each and every element we have the element stiffness matrices, and these are assembled into global stiffness matrix. Each and every element, they span between 2 nodes. For example, this 6th member spans between these global coordinates. You can see the member 6 here. Member 6 spans between 3, 4 and 7, 8. So the member 6 spans between 3, 4 and 7, 8. These numbers may change depending on how you choose the first node and second node for each and every element, or the ith node and jth node for each and every element. So when assembling all these stiffness elements, we will have the global stiffness matrix. And after establishing the global stiffness matrix, we can find the reduced stiffness matrix. Like in the sense, this is nothing but F equal to K times U. In this U vector, all these components are not actually unknowns. Some of them are known quantities. For example, 4, 5, 6, 7 and 8. These are actually known quantities. Here you can see 4 is actually restrained, so the displacement must be 0. Similarly here 5, 6, 7, 8. All these directions have reactions, so there will not be any deflections. So U values U4, 5, 6, 7 and 8 are actually 0. Similarly, the force at 1 and 2 are known quantities because they are the external given forces, whereas the force at 4, 5, 6, 7, 8 are unknown quantities because they are the support reactions. So we have some known quantities and some unknown quantities in these two vectors. So these U values are known and these F values are known. So we can reduce this matrix such that the known forces are written as a force vector. So corresponding to this, we can have a reduced stiffness matrix here. For example, this is from, these are the first, second and third coordinates. So the first, second and third columns as well as the first, second and third rows only are taken. The rest of them are eliminated. Similarly here, it has only rows. So the first, second and third rows are taken. So this is much simpler to solve. We can find what are the unknown displacements. Once we know what are the unknown displacements, you can use those values here in this entire matrix and find what are all the unknown forces or support reactions. So using the identified U values, we can find P values. Once we know the support reactions, we can find the member forces. From the tension test on mild steel problems, we know U or delta equal to PL by AE. That is a much familiar term for us. So this is similar to delta, and we have P, L, AE. And these L, M, minus M are used to resolve these displacements along the direction of the member's length actually. So using this expression, we can find the member forces. So now let us see the MATLAB program. In this MATLAB program, the first step is the number of nodes. Number of nodes are taken as input from the user. So using this number of nodes, node data is an array generated with number of nodes as the rows and 7 columns. These 7 columns uses are the node numbers x, y, x restraint, y restraint, fx and fy. Similarly, for the members, we are getting input from the user for the number of members. So using that, we are generating a member data table with the 5 columns. The first one is the member number, second one is I node, J node, A and E. After getting all these input, we are calculating the member length and storing that in the member data. This is actually length of member, square root of xj minus xi whole square plus yj minus yi whole square. I am storing this value in the 6th column of the member data. Initially I am using only 5 columns. I am adding another 6th column and adding the length of the member. After that, I am finding the direction cosines cos theta and sin theta. That is nothing but xj minus xi by l is the cos theta and yj minus yl yj minus yi by l is the sin theta. I am storing these direction cosines as the 7th and 8th columns of the member data. After that, I am trying to establish the global stiffness matrix, and I am initializing the u and f vectors, and I am assigning the known values to the f vector. Then I am initializing a reduced K matrix. Wherever we are having restrained coordinates, I am eliminating those particular rows and columns in this reduced matrix. So I am eliminating the corresponding rows and columns here. Here I am eliminating the rows and here I am eliminating the columns. In our particular example, 4, 5, 6, 7 and 8 are the rows and columns to be eliminated from the global stiffness matrix to find the reduced stiffness matrix. Once I know the reduced stiffness matrix, I can find the unknown displacements, which is nothing but the K inverse times F. Once I know the U values, I can find what are my support reactions. For that, I am using the global force vector, U vector and the global K matrix. Once I know the support reactions, I can print that, as well as I can find the member forces. So that's all. Now let us check our given inputs. For our particular problem, let us look at this picture. Node 1 is located at 5, 5, and there are no restraints here, and there are two forces. Here there is a force of 5 kilonewton and here there is a force of minus 10 kilonewton. So now we will run our program. So the first line is, it is asking for number of nodes. In our problem it is 4. So enter the details of node 1, that is displayed here using the printf command. And the input is taken as an array. So the array should be such that the first column Second column are the xy coordinates. Third and fourth should mention the whether they are restrained or not. This is not restrained. Sorry, our coordinates are actually 5 and 5 for our problem, and these things are not restrained, and the forces are 5 and minus 10 in the x and y directions. Similarly, for our second node is located at 0, 5. Our second node here, it is located at 0, 5, and there is a restraint in only in the y direction. So 0 represents no restraints and 1 represents yes. 0 means no, 1 means yes. In similar sense I have used it. There are no external forces. The third node is located at 0, 0. Both the coordinates are restrained and there are no external forces. And the fourth coordinate is located at 5, 0. Both are restrained and no external forces. And I have 6 members. Here it is asking for enter the details of number 1. You can look at these syntaxes. I have used a printf. So the member details. Say the first member is located at is between the nodes 1 and 2. Let me take the first I node as 1 and j node as 2. Let me give unique values for a and e. Similarly, for the second member is located between 1 and 4. Third member between 4 and 3. Fourth member between 3 and 2. Fifth member between 3 and 1. Sixth member between 2 and 4. If you change the order of these I node and j node, if I'm giving, for example, for the first member, if I am giving the node from 2 to 1, then the signs may change in your stiffness matrix. That's all, but the values remains the same. So now the program is finished calculating the values. The global stiffness matrix calculated in our program, it should match the value in this example. So it's actually matching. Reduced stiffness matrix is 0.27, 0.71. Yes, it is matching. The unknown displacements is 72, 55, 53, 72, 55, 53. Yes, it is also matching. And the unknown reactions, minus 3.8, minus 1.19, minus 1.19. Yes, these values are also matching with these calculated values. And the forces in the member forces, minus 3.8, 11.19, minus 3.8, 11.19. Yes, all these values are also matching. So that's all. If you have any doubts, you are most welcome to contact me.